Hi, everyone. Is this working? Hi, everyone. Thank you so much for joining. We're going to get started with today's Lunch and Learn. Ryan Foltz will be our presenter. Let's give him a round of applause.
Hi. Hi, everyone. So I don't know some of you. In case you haven't met me, I am, again, Ryan. I started here at Exabeam 3 months ago this last Tuesday, and I joined the data science team. But before I was a data scientist, I was an astrophysicist. And so I knew that I wanted to give this talk for a while. And so I've been thinking about how I want to present or what I want to present. And I think the right way to do it is that this isn't a science class or a lecture, so I've left out all of the math. And so as a result, that means I'll be telling you some things, but I won't be explaining exactly how we know these things. But of course, if you're interested, you can ask me about it. Of course, that's not how science should ever be done. You should always be able to ask why and get a good answer, right? But so instead, I really just wanted to try to convey some of the wonder that I think is what got me into this field in the first place. So specifically, we're going to set out to answer these three questions. How big is the universe? How much stuff is in it? And what is it doing? So I thought for a while about how to present this, and this is what I came up with. Imagine you are a baby. And so this is probably pretty easy to imagine, and we all were babies at some point, right? This is how we came into the world. So when you are a baby and you're new to the world, this reality is not of your making, which means that you don't really know what to expect, right? You have to learn all of it. And you're learning, what is this reality thing, this life thing that we're all in? And you can see that you have like a nice crib and you're in a room, and this is your reality. This is the universe. But you can tell that there's probably something outside of it, right? What is out there? More rooms, probably, maybe. So anyway, you grow up, you leave the room, you start exploring your area, and eventually you go to school, and somebody shows you one of these things, and they tell you that you live on a... So eventually, one way or the other, you see one of these and someone tells you that you live on a giant ball. And that's pretty weird, right? It doesn't look like a ball when you experience it. To me, it would make more sense if we lived on a giant infinite flat plane. But it's weird, but a lot of things are weird when you're a kid and you just sort of learn it and you take it in stride and you learn, okay, we're over here and your grandmother lives over here and blah, blah, blah. But it is weird. It's weird that we live on a giant ball. I mean, in our experience, a ball needs to be resting on something, right? Or else it's going to be in free fall. What is the Earth resting on? It's just a ball hanging out in space. That's very strange. It turns out it is in free fall. It's in free fall around the sun. And then so you have the nice sun that we're all familiar with. It's the bright object in the sky that you see when the daylight. And then you also have the moon that you can see sometimes. And this explains why sometimes it's light and sometimes it's dark. And that's okay. Like, you can live with that. And then eventually you see something like this, and people tell you that actually there's a whole lot of other balls out there, other planets like the Earth. This is called an orrery. And I do remember when I learned this, I was in second grade when I first saw one of these things. So there's a whole lot of planets, 8 or 9, depending on who you ask and when. And the whole situation is really strange at this point. I've shown the planets here to scale. And the point is, you can't really even see the Earth and the inner rocky planets. That's how tiny they are relative to the sun. But this is not accurate to scale. If the sun was actually this size, then Neptune and Uranus would be out somewhere on the other side of San Mateo. So that's our solar system. And we can actually see these planets. You can see them at night when you look out into the sky, because they reflect the sun's light back to us. And so they appear as these bright star-like objects in the sky. And in fact, you can see the Earth from these other planets too. This is a picture taken from the surface of Mars, and you can't really see it on the projector, but the Earth is right there. So it looks the same, right? What planet you're on. And so you can kind of get comfortable with this notion that these are the planets and okay, that's our world, right? This is the world, this is what exists. But of course, I've left a few things out on this diagram. There's a asteroid belts here between Mars and Jupiter. This is just a whole bunch of rocks that are really huge that just didn't manage to coalesce into a planet. And then there's more stuff on the outside too. Down here is our planets in our solar system. And then shown on the outside here is the Kuiper belt. And then even further out is the Oort cloud. And these are just collections of rocky, icy, dusty things that spend most of their time out there. This is where comets live when they come back and visit us and go around the sun. Okay, so that's our solar system. But that doesn't really explain everything because you can still see that there's more stuff out there, specifically all of the stars. In fact, there were debates for thousands of years about the nature of the stars, because whereas you can see the planets move around in the night sky from day to day and month to month and year to year, the stars always seem to be in the same place. So they reasoned, whatever they are, they've got to be really far away. And in fact, of course, today we know that these stars are just other suns like our own, with their own solar systems, their own planets, et cetera, et cetera. But they are indeed very, very, very far away. But we're trying to understand what is the size of the universe. So we need some way to measure how far away these things are, right? If we want to really understand it. How do we do that? Well, here's one idea. We can use the fact that the Earth goes around the sun and some geometry to establish a distance measure. The way that this works is here's our Earth, here's our sun, and here's the star that we're trying to figure out how far away it is. And we go up here to the North Pole in July, and we measure the angle between the North Pole and where that star appears on the sky. And we record it, and we pack our stuff up, and we relax for 6 months, and we come back in January, and we measure the angle again, and we see that it's changed, right? Back in July, the star was over to the left of the North Pole. Now it's to the right. That is a fact. That's a result of the fact that the star is a distance away, and you can actually use these angles then to measure that distance. So we knew that this sort of thing was possible since 1674, but it wasn't until the 1800s that anyone actually measured it. It's extremely difficult to measure this, what we call stellar parallax, because these distances are so great. These angles are so small that you need an extremely sensitive telescope to do it. So this was first measured by Bessel in 1838, and they started to map out the positions and the distances to all of these stars in our nearby neighborhood. And you see you have all the classics here. You've got Vega, Alpha Centauri, all the good ones. But these stars are really just a drop in the bucket compared to what we can see, right? There's still more out there to map. And so William Herschel decided that he was going to really do this around the same time. He built the largest telescope at the time. They called it the Great 40-Foot Telescope. And he set out to map all of the stars. He wanted to know, what does the distribution really look like in space? And if you ask me, what would be normal, what would be acceptable, would be if all of the stars were just scattered randomly through space. That would be nice and simple. It wouldn't require a whole lot of extra knowledge in physics. You could model it as a gas. It would be great. But that's not what Herschel found. This is Herschel's attempt to map all of the stars. We're down here in the middle, and already you're starting to see some weird features, right? This is not an even distribution of stars randomly scattered in space, but instead it's flattened out like a pancake. And that's really weird. His techniques were crude by modern standards, but he was already starting to detect some of the salient features of our reality. And to me, when I see something like this, it's weird. It's like if you come across a rock and it's flattened out like a pancake instead of being rock-shaped, right? There's almost some intentionality there. There's something to understand about why is it that way. But okay, this is the 1800s. Today, of course, we have this picture, which you may be familiar with. This is our modern image of where all the stars are located, that we can see with the eye. And we call this gigantic collection of stars and dust and gas, we call that the Milky Way, and that's our home. And now the picture has gotten even weirder, right? Here we are down in this little part of the disk, and we see that all of the stars are in this giant, like a pizza with a bulge in the middle, and they're all spinning around the center, and there's these spiral arms. And to me, that is very, very strange. This is an artist's rendition, but of course you can see the Milky Way from the inside when you go out at night. If you're in a really dark enough place and you look up in the sky, you'll actually see this. What you're seeing is you're standing out here on the edge of the disk, sort of about halfway out, and you're looking in through the disk. And so it appears in the sky as this bright sort of cloud. And that's just the fact that there are so many stars, all so densely packed together in our immediate neighborhood, that all of their light blends together as this sort of diffuse glow. So this is an image of what it must look like from the outside. And there you go. That's it. That's our world, right? That's nice. It's weird, but okay, we can accept that. But is it the whole world? Well, in fact, if we were living only 100 years ago and you came to a similar talk like this, there'd be some other astronomer there, and she would tell you that, and in fact, this is our whole world. It's about 150,000 light years across. It has about 200 billion stars in it. It's about 50 light years thick, and it's just sitting there swirling around in the void, and that's it. That was only 100 years ago. This is where your world would stop. But of course, I'm sort of giving away the punchline, right? The fact of the matter is, back then, there was a great debate about objects such as this one. We call this M51. This was sketched by an Irish astronomer, Lord Rosse, in 1845, and he was using the cutting edge, the biggest telescope in the world at the time. They called it the Leviathan. It blew Herschel's puny 40-foot telescope out of the water. This was the latest and greatest scientific instrument ever, and we still couldn't get a handle on what these things were. We called them nebulae. We could catalog them. We could find them on the sky, but they just looked like these swirly blobs. Today, of course, this same object, M51, as photographed by the Hubble Space Telescope, looks like this. This is how it appears to us today in 2005. So Lord Rosse was doing a good job, right? I mean, that's pretty accurate. But now, of course, with the benefit of modern techniques, modern astronomy, we can see that this is a whole other galaxy, just like our Milky Way. So another few 100 billion stars, each with their own solar systems, potentially with their own life like ours, all swirling around their center. And in fact, there's a lot of examples of these. This is the Andromeda Galaxy, as photographed by Hubble in the 1920s, and again, as photographed by an amateur Hungarian astronomy just in 2009. And it's incredible to see the advancement in our techniques, but also to think that overnight, our entire concept of the scale of the universe just exploded, right? Now we are not just one star among a galaxy, but now we are one galaxy among uncountably many. Andromeda is actually really close to us. It's our closest galactic neighbor, close in a relative sense. It's about 2 million light years away. But if you could see it on the night sky, it would be about 3 moon lengths long. That's how big and how close it is. So in fact, there are several galaxies in our immediate neighborhood. We call this our local group. Here's us in the Milky Way, and here's Andromeda. But there's also a lot of these dwarf galaxies, and you see they sort of clump up close to us. They're pulled in by our gravitational pull, and they are satellite galaxies. You may have heard of the Large Magellanic Cloud and the Small Magellanic Cloud, but there are plenty of others. And so this is our local neighborhood of galaxies. And we can zoom out even farther. our local group is here in this image, and you see we are on the outskirts of something far more massive than we ever imagined before. And it's worth pointing out at this point that in this sort of diagram now, all of the single points on the plot aren't stars anymore. They are entire galaxies. And we see that galaxies clump up and associate into these massive structures, all held together by their mutual gravitational pull. We are closest to the Virgo cluster, and the other clusters you should know in our neighborhood are the Fornax cluster, and then there are others. But we sort of lump the all together into one large thing that we call Laniakea supercluster. And we can zoom out even farther from that. Oh, this is what Virgo looks like through a telescope. And all of these points that you see are entire other galaxies, right? Just like our own. Every little point that you see in the distance, these are not stars anymore that we're looking at, but galaxies. So if we zoom out even farther, the superclusters clump up even more into larger associations. So here's our Virgo supercluster that we were just looking at, and we see it's next to all these other superclusters, Centaurus and Ursa Major and so forth. They're named after the constellations that they appear to be within on the night sky. And we're starting to see the hints of what we call the large scale structure of the universe. This is what the universe looks at the very largest scales possible. And I'm showing you here actual data as observed by several large astronomical surveys, such as the Sloan Digital Sky Survey or the 2 Degree Field Survey. Every single pixel in this plot is another galaxy, or in fact, sometimes multiple galaxies. And you're starting to see the really strange structure that emerges. There's these clumps like this. These are the superclusters. There are the long, thin filaments that connect them all together. And they all surround these massive voids of totally empty space. The large scale structure, when you zoom out far enough, you've reached the end of structure, meaning that if you zoom out more, you're just going to see more of this. At the very largest scales, it just looks like a featureless foam of stuff. So that's what the universe looks like from where we're sitting. And I wanted to answer, what is it all doing, right? This will put us on the way to answering those 3 questions. So this is kind of the only sciencey part that I said I was trying to avoid. But it turns out that when objects are moving away from us or moving towards us, it kind of bends or stretches the light a little bit. We call that redshift or blue shift, such that objects that are moving away from us, their light becomes redder. We call that redshift. Objects that are moving towards us, their light is blue shifted. Their light becomes bluer. So you can use this. We can measure the speed of all those galaxies and look at how they're moving around in our neighborhood. And in fact, this is what people like Hubble were doing in the 1920s and 30s. And they find something extremely weird. In this plot, this is the velocity that the galaxy is moving away from us. And this is how far away that galaxy is from us. So first of all, everything is moving away from us. Every galaxy that we see, except Andromeda. And the farther away a galaxy is, the faster it's moving away from us. This should really trouble you. It makes it sound like we're down here in the center and somehow everything knows to run away from us specifically. That is a really bizarre fact, right? Like, that's difficult to explain, difficult to deal with. But here, okay, you can see this. I want to demonstrate one possible explanation for this bizarre fact. So here are 2 images of dots. We're going to say all of these dots are galaxies. And I've taken this image and I've just stretched it out just a little bit. And now if we are living in a universe of galaxies that's all being stretched out, and we live in, say, this purple dot, then it will seem to be in the same place after it stretches a little bit. And what you see is that all of the dots now seem to be rushing away from the purple dot where we live. This is because I've stretched out the image, right? And the more distance there is between me and the other dot, the more it expands. There's more distance to expand. So the farther away it is, the faster it's expanding away. And it doesn't matter what dot you live in. We could live in the green dot. So let's try that. You live in the green dot, you see the same exact thing, right? So there's nothing special about our perspective onto the world, even though it seems everything is rushing away from us. This is simply because that space is expanding. This is another analogy that you sometimes see, the raisin bread model. I like my diagram better, but the idea goes, if we're all raisins, galaxies in this lump of dough, as the dough rises, all the raisins are carried away from all of the other raisins equally, right? This is weird. This is a weird thing. But we've known that space can expand ever since Einstein did his work. In fact, we expect the universe to either be expanding or contracting. It's not really a surprise once you know about that. It's a general prediction of our understanding of space-time. But that doesn't make it any easier to accept that space is actually something with properties and it can stretch and expand. I mean, I really want to emphasize this point. This isn't that the galaxies themselves are moving like they're coming out of an explosion. This is space itself is growing, meaning that there's more space today than there was yesterday. And so what does that mean about yesterday? Well, that means there must have been even less space the day before that. And it's through this sort of reasoning that we can work backwards towards the prediction that there should have been some sort of Big Bang thing. And if you run this calculation, it tells you that the universe has only been around in its present form for about 14 billion years. Again, I'm not really explaining how we know this stuff, but this is the prediction, and we see it confirmed in a dozen different ways. So, yes. Same amount of stuff, just more space. It's like we're on the surface of a balloon and the balloon is being inflated, or we're a raisin in a lump of dough and the dough is rising. So yeah, there's more space, more distance between things. So if the universe began then 14 billion years ago, then we should never be able to see anything that's farther away from us than 14 billion light years, because that stuff wouldn't have had time for its light to reach us yet. So this ultimately defines and answers that question of how big is the universe, or at least how big is the observable universe. Here we are down here in the center, and then just draw a gigantic sphere 14 billion light years in radius, and we call that the observable universe. You'll never be able to see anything outside of that bubble. You'll never be able to be affected by anything outside that bubble, because nothing can travel faster than the speed of light. And you yourself will never be able to get out of that bubble. So that's our observable universe. Someone somewhere else would have a different observable universe centered on them. And all we can do is guess that it would probably look more or less like what we see around us. As to whether it's infinite outside of this bubble, we don't know. So that's the size of the observable universe. And once you know that, you can start to estimate various other things. Oh, to put a number on it, 14 billion light years is about 1.3 times 10 to the 23rd kilometers. But it doesn't even, you can't wrap your head around a number that big or a size that big. So I don't even try. I can barely understand how big the Earth is. So at this point, I just kind of, let the numbers go. It's really big, right? Basically, that's a really big number. So when you know that, and you know a few other things, you can start to estimate how much stuff is in it as well. Overall, the universe has a very, very low density, 3 times 10 to the negative 30 grams per cubic centimeter. And I think this works out to be about 1 molecule per cubic meter over the entire universe. Right? Around here, the density is much higher than that, but there's so much more space than there is stuff that the density drops a lot. And then that amounts to a total mass, or total amount of stuff, of 3.4 times 10 to the 54 kilograms. And again, that's a very large number. It looks like that. I don't know if that makes it any easier to understand. So there you go. That answers those questions that we set out to answer. How big is the universe? The observable universe. It's about 14 billion light years in radius. How much stuff is in it? Well, there's that much stuff. And what is it doing? It's expanding. So that is really what I wanted to convey today. And hopefully you agree with me that this is a very strange set of circumstances to be involved in. But here we are. This seems to be the case to the best of our knowledge to date. And hopefully tomorrow we understand even more about it. But I do think it's very strange. And I just wanted to hopefully communicate that some people have this idea that when you learn the science behind something, it takes some of the beauty or the poetry away from it. But I disagree completely. The more I learn about the universe, the weirder and trippier it all seems to be, right? So those are all my slides. So thanks for coming to my lunch and learn. Yeah, Daniel. Yeah.
And there were like 2 points of a lot of light. I'm just wondering what that second point is. That's not centered.
So that's another galaxy. That's a dwarf galaxy that's either being sucked into M51 or M51 is being sucked into it. But galaxies frequently collide and merge. So we see that when we go looking. And I also thought that was interesting because Lord Ross, he got that right there. What other questions do you have? I don't have all the answers. Yeah. So that's a good question. And sometimes it's not easy because galaxies can be very round and very far away and they can look like a star. But generally, galaxies are going to be so much fainter because they're so much farther away. Like the most distant star in our galaxy will only be 150,000 light years, but the closest galaxy is 2 million light years away. So they're going to be a lot dimmer. And that's really the reason why we didn't really understand this stuff until about the 1920s or so, because you need a big telescope to see that far. Does that make sense? Yeah. Mm-hmm. Yes. Yes, absolutely. That's good. The center, we always look at spiral galaxies because they're nice to look at. Spiral galaxies concentrate most of their mass in this central feature that we call the bulge. And yeah, that's billions and billions and billions of stars. If we were down in here instead of out in the disk, we wouldn't really have a dark night sky. Like that's how many stars there are. So yeah, all of the stars, we are orbiting around it just like the planets orbit the sun, but that's mostly due to the total gravitational attraction of everything in there. Whereas in our solar system, it's all basically just due to one star, right? The other interesting thing about the central bulge is that we've learned only as recently as like 10 years ago that pretty much any galaxy you look at like this has a supermassive black hole in its center as well. So instead of orbiting a giant star, we're kind of all orbiting a giant black hole. But that's a subject for another talk, I guess. Oh, John Ying.
So how do we estimate?
You're really getting me there. That's part of the really tricky cosmology stuff. But basically, it comes down to once you know how space behaves, and you know how fast space is expanding, and we know how space behaves because we have a theory, general relativity, we can work out from all the cosmological parameters that we can observe how much stuff there must be. And there's a few other methods. There's several, I think 3 or 4 independent mass measurements, and they all roughly agree. Some of it is cosmic microwave background radiation stuff. And it's cool, but it's beyond our scope. Yeah. Yes. Yeah. Yep. Well, we won't be able to if it's 28 billion, right? The observable universe, this is the key. Like the actual full thing of what exists has got to be much, 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 much bigger than this, right? Much bigger than 28 billion. But if you're asking why can't we include something 28 billion light years away in our observable universe, well, that stuff, the light to reach us would have to travel 28 billion years because it's 28 billion light years away. But the universe has only been around for 14 billion years. So that light hasn't reached us yet. Does that make sense? There's a limit to what we can see because there's a finite age of the universe and a finite speed at which light travels. Okay. Right. Yeah. Yes. In the back. Yeah, actually, if you look back to the very early universe, we see differences between our clock and their clock. You can actually detect differences in the way that time has passed in the past versus the present. And that's one of the ways that we know that this is a stretching of space-time rather than just like light just naturally gets redder as it travels or whatever. That's a good question, though. You had a question? That's a very good question. I think, okay, so the question is why does nobody call and why does nobody visit? If we go back to our Milky Way, and this is something that has been talked about in physics for a while. It's known as the Fermi paradox because even with like just barely advanced technology, say we could move on and colonize the next closest star and spend, you know, a few thousand years to kickstart civilization then, and then send out more ships to colonize the next closest star. At most, you know, that would only take 100 million years to colonize the entire galaxy. Even 200 million years, whatever. That's a drop in the bucket relative to the length of time that our Milky Way has existed, which is some 10 billion years. So the question is, why isn't it colonized yet by some form of life? A lot of people have a lot of answers. I don't think anyone really knows. I think the real truth is we can't really say anything about that yet because even our most advanced searches for technological life out there, they're not that advanced. Like we've really only scanned one tiny little bit of the sky and only so far out. And it's extremely limited what we've done so far. Some people say that if we're ever going to contact alien life, it'll be in the next few decades, or else we'll never contact alien life. I don't know. Cool. Oh, thank you. All right, cool. All right, yeah, hey, I'm Ryan. Ina? What do you do? Oh, okay. Okay. I'm in